Okay, this is lecture 17, and we're going to continue on our progress here to work on the gradually varied flow processes, natural channels, and we're definitely going towards getting everything that we need to be able to apply the standard step method. And in this lecture, we're going to spend some time on dealing with the natural channels, the factors that we have to take into account for natural channels, which is the expansion contraction losses and the energy correction factor. And then we will introduce the standard step method. So this is the energy equations which you've been accustomed to up to this point. This is the total energy at a particular section H, and you've got the potential energy, the pressure potential, which is also the depth, and then we've got the kinetic energy, and you'll notice here that we have the Coriolis, or the energy correction factor, the energy coefficient. And so what you're going to see us do here is that we're going to combine the potential energy and the pressure potential into one term, and we're going to call that the water surface elevation, W. Now, if we look at the change in total head with respect to location, dH dx, that is basically the slope of the energy grade line. And that slope of the energy grade line is made up of the friction slope and slope due to expansion contraction losses. So far, like in the direct step method, all we worried about was the friction slope. But now we're also, because this is natural channels and you're going to have expansion contraction, we're going to spend time thinking about the expansion contraction loss. So if we look at the a side view of what we've got here for a channel, if we look at this as our bed right here, and we've got some off of the datum, we've got some water surface elevation, and we've got another water surface elevation down at the second location. Again, this is a combination of the depth and the potential energy. And then above that, you've got the velocity heads. And notice again, we've got the Coriolis coefficients. And then this difference between the energy at location 1 and the energy at location 2 is our head loss. And that's comprised of the head loss due to friction and that due to expansion contraction. Now, as we look at this and we develop this, we've got this whole business where we've got the derivative of the energy change, total energy change with respect to X, and that is the change in the water surface elevation with respect to X and the change of the velocity head with respect to X. If we've looked at this in the prior definitions, we had that energy change with respect to X, or the change in the energy with respect to X, total energy, was this friction slope and the expansion contraction slope. We can put them together and we have this form of the equation. Now, again, remind you that we're going to use Manning equation to evaluate this term of the friction slope, and that we've introduced this concept of conveyance, K, which is simply the first part of the Manning equation except the friction slope. So we have to compute an average value for the friction slope, as we covered in the direct step method. And there's multiple ways to do that. There's simple averaging of the conveyance values and using that to calculate a average friction slope. There's an average conveyance that is of this form here, where you've got the total flow rate squared, and then you divide that by a combination of the conveyance terms, upstream and downstream. You've got what the USGS uses, which is the geometric average of the friction slope calculated at one section times the friction slope at the other, and then we take the square root of that. So there's a number of ways to get at this value of average friction slope. And what I found over the years is that really they make very small differences. I suppose in some cases there might be. You can use, when you get into using HEC RAS, which is the program we're going to use to do the automated computation of these things, there are multiple choices you can make in terms of how you compute the average friction slope. Now, when we talk about dealing with the expansion contraction losses, what we end up applying is we do a change in the velocity head. So, and this is pretty standard in any of the applications. If you remember when we were looking in your fluid mechanics, we had pipe flows. We had the losses due to in CE 33330 fluid mechanics. You dealt with pipe losses, and you had some coefficient times the velocity head. I don't know if you remember that, and we summed up those coefficients to get the head loss, the minor, what they call the minor losses, and this is analogous to that in open channel flows, but it's not quite the same. But we do use a coefficient, and we, instead of taking the velocity, because we know it changes from one location to another, usually in pipes, the velocity, the pipe diameter stays the same. So you got a flow going through a pipe, and the diameter stays the same, so the velocity doesn't change. Here we know that we've got expansion contraction, so the velocity from one location to the next is going to change. So we take, and you notice here we got the absolute value, we take the difference between those velocity heads, and then we multiply it by this, this coefficient. Now this is the slope of that expansion contraction, and if you have a contraction, it's going to be one value, expansion is going to be another. And you'll notice here that when the velocity downstream, the velocity head downstream is greater than the velocity head upstream, that's going to be a value that's going to be a contraction. And here where you've got the velocity head downstream is smaller than the velocity head upstream, that's going to be an expansion. So you'll see C sub C and C sub E, and those are going to be different values. I can tell you that it's much more efficient, and so therefore less energy loss when you have a constriction versus a contraction. And so if I'm looking in plan view and I'm contracting the flow and it's going this way, this is a much smoother transition to coming together in this area where we've got the contraction than if I have the other situation where I have an expansion. And so when you have flows downstream, it gets in here and you have these big eddy vortices that form up here, and you'll see whirlpools and things like that. This is a much bigger amount of energy loss in this expansion than you would have in the contraction. And so these values of the coefficient are going to be larger for expansion than they would be the contraction. So if we look back at the equation development, this is from a few slides back. You've got the total energy losses, the slopes, and we've got this in terms of a differential equation of the change in water surface elevation and the change of the kinetic energy head. And so if we kind of expand that a bit and we use this as our form, this is again the average conveyance method to getting the average friction slope right here. So this is this business right there. We leave the energy slope due to expansion contractions alone for a moment. We look at this, dW dx is nothing more than the change of the water surface elevation over some distance. And then the same thing with the derivative of the velocity head with respect to x. We can expand that, we rearrange, and we're basically just exploding it back out into an energy form. And you'll notice this right here is our head loss due to friction. So head loss due to friction. And this is going to be our head loss due to expansion contraction. So this is the form of the standard step method. As we get into this, we'll look at developing this. So this is just from the previous slide. And you can see as we move through here, we've got 1 and 2. If I want to make this more generic where I've got upstream and downstream, I can use subscripts of K and K plus 1. So the K plus 1 is the downstream, the K is the upstream, and we have that as the nomenclature. So this is going to be the form of much of the standard step method, although we're going to expand this out in a second here later in the lecture, because we're going to really start talking about this, put back into context how we account for the expansion contraction. Now I want to deviate just slightly here and talk about the Coriolis coefficient, or the energy correction factor. And we need this because we end up using the mean velocity for the most part to estimate the kinetic energy. So we have the mean velocity squared divided by 2g. That is our estimate of the kinetic energy per pound of flowing fluid, right? Pound of flowing fluid. And so we know that that is not always a good estimate. And so if we really wanted to have an accurate estimate of the kinetic energy, the total kinetic energy in a cross section, we would integrate over the area of that cross section. And so we've got the little v here, which is the velocity at all kinds of different locations. And we know that varies across the channel, and we integrate that over some area. So if we've got, you know, a cross section, if I look at that, here's my water surface, and I take some little area here where I've got some small velocity, and it's an area of dA. If I take all the, you know, discretize this into small little infinitesimal parts, which is what the integral does, I could come up with a really true estimate of the total kinetic energy. Now, what we're doing to estimate the total kinetic energy with the mean velocity is this, where we take the total area and the mean velocity and take it to the cubed, and we end up getting an estimate of that total kinetic energy. The alpha is a fudge factor. If we can take and if we rearrange this and put the a v cubed over on the other side, we'd have alpha a v over bar cubed is equal to integral of a little v cubed dA. What you can see here is this alpha is making up for the air that's that we incur if we just use the mean velocity cubed times the total area to estimate the total kinetic energy. So it's really like a fudge factor. And so when I rearrange this, and we can or go back to where we're at up here, and we get this into discrete terms instead of an integral, you know, it's basically a summation of, if I broke this up into little integrals, if I just broke it up into, you know, say 3 cross sections, 3 sub areas. So this is A1, B1, this would be A2, V2, A3, V3. I could come up with a value for that kinetic energy correction factor, the energy correction factor, using that. The problem is going to be that we do not have a priori knowledge of these velocities to be able to estimate this. When we're doing this modeling, we don't know what the velocities are because we're modeling it. Once we know what the depths are, we can estimate the velocity, but we don't know a priori. So we're going to do something about that. So if we look at 3 subsections, this is what I had earlier. We broke these into 3 subsections. And if I look and say, okay, well, if I want to look at what is that mean velocity, well, that's nothing more than, you know, basically taking the velocity V1 here and A1 and the V2 and then the A2 and V3 and the A3. If I sum the product of those up and divide by the total area, this is nothing more than Q over the total area, right? That's what the velocity is. So if I take this and we basically rearrange and say, okay, well, I can say that VI is equal to big QI, which is the discharge in that section. So this has got a Q1, this is a Q2 and a Q3. So total Q is equal to Q1 plus Q2 plus Q3. And so if I look at this and say, okay, instead of having VI, I'm going to show that as QI over AI. So that goes right there. And then I leave the little AI alone. And then instead of just showing the mean velocity here cubed, I end up showing the mean velocity in this form right here. So there you go, stuck it right there. We cubed that. And then instead of showing total area, I show that as the sum of the little areas AI. So far so good. We've gotten rid of the velocities right now. We've got them in terms of area. Now, if I go a little further and I remind myself, do a little expansion on this and rearranging, so I end up having this this form of the equation for alpha. But I remind myself that basically the discharge is nothing more than the conveyance of that. So, you know, what is the discharge in section I? That's nothing more than the conveyance in section I times the friction slope in section I. If I can make the assumption that the friction slope in one section is equal to friction slope in another section, which is equal to friction slope in the third section, well, I can then get by with saying, well, Q1 over K1 is equal to Q2 over K2, Q3 over K3, and I can make some substitutions in there. So I'm going to basically get rid of some terms here. And so I've got, this is from the previous slide, and I rearrange and I can put substitutions in for things, and I can plug these two relations together, and I end up getting this is my equation for that, because I'm now, if you remember, we had this form right here, this big form, which was kind of messy, and we wanted to show some things, getting rid of it. And so we bring that out, and we end up simplifying it and reminding ourselves that we can, instead of the Q, we can substitute that in for this and this, and we end up having, this is the form of our alpha that we use for computing the correction coefficient in any application we're going to have. So none of this means that we have to have knowledge of the discharge, or I mean, not the discharge, but the velocity a priori. We can just enter it in a very simplistic way. All right. So there's just a form where we're now no longer showing it as this. We're showing that's the total area. This is the total conveyance. Okay, so we'll now move to an example problem, and you can look at that.